cloud physics they use, but so with and without, we can see the much heavier convection develop before making landfall. So this is the precondition. So we are trying to, this observation, this modeling study also confirmed with observation that this convective activity was established prior to making landfall. It was established much earlier. And now I would like to move to the next topic to share with you how we observe Western North Pacific. It's a very complex ocean. This usually you can't see. Taiwan is here, you cannot see, observe from the sea surface temperature because everywhere is warm. But actually, if you're using the satellite altimeters, which you can see that this is actually a very complex ocean. Taiwan is here. This is a southern eddy ridge zone and the northern eddy ridge zone of the Western North Pacific. This is a special ocean with many mesoscale ocean eddy activities, with both warm and cold eddies here. So these eddies are suggesting difference in the subsurface warm layer, with deeper subsurface warm layer or thinner subsurface warm layer. And with SST you can't see very much. Okay, but actually it is not uniform. But it is actually very complex. So you can tell this is an observation. If you want to extend this observation to the Eastern Pacific, it's flat comparatively. You can see that Taiwan is here. We are having all these activities here dynamically. This is a very Western Pacific Ocean can show that how vast and complex it is, and this is in contrast the the Eastern Pacific Ocean. And this is also a region with most number of Category 5 storms in the world. So we did a study. With Junjie, we want to study how these Category 5 storms interact with these ocean eddies. We did 13 years of observation between 1993 to 2005, and we found that, without exception, all Category 5 storms develop at this region encounter warm ocean eddies. Okay, this we published in the Monthly Weather Review in 2009, and the reason is this. This is the warm ocean eddy region, and this is the without ocean eddy, the climatology region. We can see that with the warm ocean eddy, it can deepen the ocean layer, subsurface layer. The heat content can be increased by more than 100%. Okay, so as such, this is the ocean, this is the background. This is actually a very shallow background for Category 5s. It is not sufficient in itself for providing environment for intensification for Category 5. However, the fortunate storms, when passing over this warm eddy ridge zone, they have a chance to encounter these warm eddies. So these warm eddies will act as a temporary boosters. They can temporarily increase the upper ocean heat content so that it can provide sufficient heat fluxes for intensification. This is the red is the with eddy run, and the light blue is without the eddy run. We can see that this is intensification from Category 1 to 5. Without the eddy run, we can see that there will be no fluxes at Category 3 or so. You won't be able to, the fluxes will go to 0. There won't be flux for intensification. So this shows the importance of criticalness of warm ocean eddies with Category 5 typhoons in this region, typically at the location between 20 to 26 degrees north. And move on, I would like to share with you the variability toward the south of this eddy ridge zone, which I call it MDR of the Western Pacific, the main developer region of Western Pacific, between 10 to 20 degrees. This is usually the region of the deepest warm ocean in the world. However, this ocean can become much shallower due to ENSO. This is the ENSO condition as observed by satellite altimeters. You can see that this is all negative. This is a big ENSO event. You can see that with the warm water howling back, going back to the east, you can see that the upper ocean, the depth of 26 degree isocene or upper ocean heat content, this is the regular condition, this is the ENSO condition. It can drop drastically You don't see so much differences in the sea surface temperature, but you see huge difference in the subsurface. The heat content can be dropped by 40%. So this is a huge drop in the precondition. So how does this affect a storm's development? Of course, this is not favorable, right? Originally, you are having such a nice warm background with strong heat content for intensification, but during the ENSO period, this place is much shallower. And we observed that actually this has a big impact on the slow-moving storms, but not fast-moving storms. I will explain to you why. This is a depth temperature profile during the ENSO condition. We can see that the shallowing from the climatology values, the shallowing of the ocean heat content. However, during that time, we also observed there are few Category 5 storms able to develop into Category 5 under such an unfavorable condition. And so, why? We observed that they were actually very fast-moving storms. The translation speed was fast. So we do a numerical study here. This is during the shallowing waters, during the ENSO condition, and this is the regular conditions. We can see this is according to the translation speed between 1 to 10 meters per second. So we can say slow translation speed all the way to the fast translation speed. We can see that because if a storm with the shallowing water, and if the storm is moving very slowly, the negative feedback from the ocean's negative feedback with the upwelling and the cooling will be much more enhanced. So there won't be enough flux for intensification. You can see that if a storm is moving at between 1 to 4 meters per second, there won't be fluxes for intensification. However, if the storm can be traveling fast enough, for example, in this case, these are moving at 6 or 7 meters per second, the ocean negative feedback has less time to respond. So it will be able to still provide sufficient fluxes for intensification. So during the ENSO period, it matters to the slow-moving storms, but not the fast-moving storms, because the fast-moving storms are able to move quickly, and the ocean will not have time to respond. So it will still have sufficient fluxes for intensification, because the negative feedback will not kill the storm. But if during the ENSO time, when the ocean is shallowing and the storm is moving slowly, then it will kill itself. What I mean by killing itself is that because the storm itself will induce this so much cooling, there won't be enough flux for continual intensification for Category 5. So with this complexity, we have this complex ocean, very dynamically evolving all the time. And with eddies here, Taiwan is here, and these are Taiwan here with all the Category 5 storm and intense storms. We are going to have a big experiment this summer. This experiment is called ITOP, Impact of Typhoon on the Pacific. This is a joint research program between